Welcome to today's electronic design webinar entitled Stability, Not Chaos, PDN Measurement That Matters, sponsored by Electro Rent in partnership with Tektronix. I'm Bill Wong, Senior Content Director with Electronic Design and Endeavors B2B. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit the questions in the question window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. As a reminder, for a better view of today's event, you can click in the upper right of the presentation and media player windows to expand them. Refer a colleague to today's discussion, share it on social media, or access event resources by clicking on the icons in the left side rail of your screen. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next 24 hours. You'll be notified by email when the archive is available. Now let's meet our presenter. James, quote-unquote, bald engineer Lewis is a senior technical marketing manager at Tektronix. He operates the intersection of power converters, PDNs, and oscilloscopes. He's helped teams clean up noisy rails, fix sketchy probing, and actually sees that their power delivery is doing what the power delivery is doing in the real world. From DC to DC design to next level scope workflows, James breaks down complex PI concepts into, oh, that makes sense, moments. If stable rails, lower noise, and cleaner measurements are your vibe, you're in the right webinar. Now let me turn things over to our presenter. James, the floor is yours.
Thank you very much, Bill. Welcome, everybody. So one thing I want to start off by telling you is that this is actually part 3 of a 3-part series. In the first part, we covered power measurements in modern systems. And in that one, we covered measurements like power quality, harmonics, switching losses, and we even showed how you can do magnetic analysis with an oscilloscope. In the second part, we focused on digital power management. And there we showed measurements like how to measure power rails properly, characterizing turn on and turn off times. And we also talked a lot about how to measure low currents with a very low noise current probe. In this part, we're going to talk about power delivery or distribution networks. I'm going to spend a little bit of time going over frequency response analysis and basically show how Bode plots can tell us things like what's the stability of our power converter, how can we measure output impedance using an oscilloscope, as well as I've got a comment about power supply rejection ratio. And then at the end, I think even for those that are veterans in designing PDNs or making PDN measurements, I've got something cool to show where we actually combine signal integrity and power integrity to show how jitter from a power supply can make its way into a target system and a measurement where you can see what it would look like if it wasn't there. Now, before we get started with that, I'm going to pass the presentation over to Leon, who's going to tell us about one of our partners, Electro Rent.
Thank you, James, and thanks again for joining us for today's webinar with Tektronix and Electro Rent. Before we begin, I just want to remind people who we are at Electro Rent. At Electro Rent, while we don't make the electronic testing equipment that engineers use, we do make it easier for organizations to procure and manage their test equipment. With an inventory of more than $1 billion and 11,000 product types, we carry test equipment from the top OEMs across the globe. Our global reach means our inventory and our people are located where your people work. Electro Rent provides end-to-end solutions for the complete test equipment lifecycle across various industries, including those represented at the bottom of the screen. Rent, lease, or purchase your equipment. And with that, I will hand it back to James for the rest of the presentation.
All right. Thank you, Leon, and thank you to Electro Rent for sponsoring this webinar. All right. What is a PDN? So a power distribution network or power delivery network looks like this. You have some kind of source and you've got some kind of load. Now that load might be a simple device like a single transistor, or maybe it's a complex device like a microcontroller or FPGA. The source is going to be some voltage source. In this presentation, I'm going to treat that as DC to DC. I mentioned in part one, we talked about some power measurements that are actually covered in terms of AC to DC. So for today, when I talk about sources in a PDN, I'm talking about another DC rail. Now, a PDN is all of the stuff that goes between those 2 points. And so you might have a regulator, which is usually called a VRM. You're probably using a printed circuit board. And then I mentioned the load, which is usually on some kind of silicon inside of a package. Now, VRMs and PCBs are interesting to me anyway, because especially the VRM will have an output filter with an inductive and capacitive element. And so those will help to define what is the output impedance of that VRM. The PCB has traces, which means there's going to be traces or power planes and vias. Those are going to have resistive, inductive, and capacitive elements as well, which will affect the impedance of our total PDN. And then finally, don't forget that any device you have, it's going to have packaging, and then there's going to be some kind of silicon or die inside that packaging, and all of those are going to have impedances. And so one of the things we worry about when we measure or when we design and then measure a PDN is how flat is the impedance across frequencies, because that's where noise can kind of enter into our system. So in the presentation today, we're going to really focus on 4 measurements. How do we measure the stability of a control loop, PSRR, impedance output, or output impedance, and then power supply induced jitter. Now, 3 of these measurements rely on a Bode plot to deliver information. And so I do want to spend just a minute to talk about what a Bode plot is for those that might be new to these kinds of measurements and the information that we can get out of them. And so just in case you need a refresher on Bode plots, they are basically a way to look at the frequency response of a element, a circuit, or a system. We typically use them to look at linear time invariant systems or elements. The x-axis will show us frequency. The y-axis will be some kind of magnitude. Both of these are plotted on a logarithmic scale, which gives us a lot of detail, especially when we look at a magnitude value such as gain. So in this case, we're actually looking at what is the gain or loss through a device under test, with another axis plotting the phase change through that device. All right. So to create this plot, we need to have some kind of generator. Typically, it generates sine waves, and then it sweeps across frequency that gets picked up by a receiver that generally has 2 channels. And one of those channels will receive a copy of the signal that went into the device under test, and then the other channel will receive the signal after the device under test does something to it. And so with this, we're able to plot out a frequency response of this system. So some of you probably already can look at this and tell what kind of device it is. If not, let's walk through real quick just to understand what we're looking at. So on the left side of the graph, I'm focused on the gain or the magnitude measurement from DC to 1 megahertz. This is essentially flat. I'm just going to call it flat at negative 50 dB. So that tells me that up to 1 megahertz, the device under test is not allowing signal content to get through it. Once we get past 1 megahertz, then we see the gain start to rise up to about 0 dB. And after around 3 megahertz, it's 0 dB. And remember, 0 dB or decibels are a ratio. 0 dB is 1. That's telling me that high frequency content is getting through the device. So what is this device then? It's a high pass filter. It has a need frequency around 2.4 megahertz, and that's exactly what the Bode plot shows us. It blocks low frequency and passes high frequency. Now, generating a Bode plot, there's 3 ways that I've done it, and these are the 3 that I can think of. If you have a spectrum analyzer with a tracking generator, a spectrum analyzer is already showing magnitude versus frequency. Tracking generator essentially gives you a known signal plus the response. So it's effectively a way to make a Bode plot. Now, if you are a frequency domain person, a more common tool to use is a vector network analyzer. These have 2 ports where the ports can be both a generator and a receiver, and some have a built-in bridge so that one of the ports can both generate and measure what's getting generated, which allows us to do the input and output measurement. There's also a version of VNAs called a frequency response analyzer, which is essentially 2 receivers plus a generator output, similar to what I showed. Now, I'm a time domain person, so of course, my favorite instrument to do Bode plots is an oscilloscope, and to do them with an oscilloscope, you need a function generator. And it is totally possible to have a separate function generator and oscilloscope, and using pen and paper and dialing frequencies to draw out a Bode plot on paper or maybe with a spreadsheet. Personally, I like to use a scope that has a built-in function generator because that usually means there's going to be software that automates the process. And like in the case of a Tektronix oscilloscope, we even use our unique spectrum view capability to get finer resolution on the measurements. We're not just relying on amplitudes. Now, one thing I will point out is that even high-end oscilloscopes are limited on their waveform generators. They typically only go up to about 100 megahertz. We do have the ability with ours to use external generators to go to 500 megahertz or even 1 gigahertz. And so this is just an example measurement. So this is where we've actually done a Bode plot. If we zoom in on the plot, you can see we go from about DC all the way up to 1 gigahertz. And that's because we're able to control an external generator, but still treat it like it was our internal generator. I just wanted to mention that because I think a lot of times when people think Bode plots and oscilloscopes, they tend to think low frequency, but with an external generator, we can go faster. Now, once we get into this frequency response analysis using Bode plots, the 3 main measurements we look at are the control loop, PSRR, and output impedance, which is what I'm going to cover next. All right, inside of a voltage converter, in a voltage converter circuit, you'll typically have some kind of switching element and then an inductor and a output capacitor. These are essentially trying to create the DC rail for our V out. There's also a feedback network, which is what feedback network so that the controller can monitor what's happening on V out. And for those of you that are new to either switch mode power supplies or even PDN measurements, I just want to point out something that sometimes gets overlooked. While R1 and R2 look like just a simple voltage divider, they are much more than that. They're not just a DC signal of what is the output. These are the input to the error amplifier inside of the controller. And so the control loop really needs a high quality copy of that divided signal so that it can respond to changes that are happening on V out. And then with that, we need to understand what are the limits that this controller can handle so that we can make sure that it stays stable. And the way that we characterize that is with 2 measurements called gain margin and phase margin. So normally when you do this measurement, you want a gain plot and a phase plot to be on the same graph. But for illustration purposes, let's look at gain and phase separately. So gain is on the top and phase is on the bottom. And remember, this is the gain and phase of the control loop for a controller. In a minute, I'll explain how we actually get to that measurement, but I want to talk about what we're looking for first. So the first thing we want to look for is what is our gain margin, which is going to tell us how much change can the controller handle before it becomes unstable. And so the way you find gain margin is you actually have to look at the phase plot. And so you look at, on the phase plot, which frequency is where the phase passes negative 180 degrees, or sometimes you'll hear people call that where the phase wraps around. That frequency on the gain plot tells us the gain margin. So you would go back to the gain margin and you would look at what is the magnitude at that frequency. And so if that magnitude is at least 10 dB, common knowledge says that should result in a very stable converter. For phase margin, it's a similar process. To find the phase margin, you actually look at the gain graph and you look at where does the gain cross 0 dB. That frequency on the phase graph, minus 180, tells you what the phase margin is. And ideally, you want to see at least 45 degrees, and the closer to 90, the better. Phase margin is how fast the control loop can respond to a change. All right, so let's take a look at a real example where the graphs are actually, hold on. Let's talk about how we actually make that measurement, and then I'm going to show you a real example of how we can make this, how we make the measurement. So what's the first thing we need? Well, we need a device under test, and there's one particular thing about the device under test that we have to have access to, which I'll get to in a second. And then we also need an oscilloscope, ideally one that either uses a built-in function generator or can control one externally. And then we need a special tool called an injection transformer. And this is literally a transformer or device that will take the sine wave that we're outputting from the function generator, and it will inject it into our control loop. And this is where the one critical thing is that you do need a small value resistor, something that is relatively small compared to the feedback network, but relatively large compared to the output impedance of the converter, where we can inject a signal into it. And so the idea is, like, if you have like a 5 ohm shunt resistor in the control loop, or what I meant to say is in the above the feedback network, we can inject a signal, and then we can see whether or not that signal affects the control loop or how it affects the control loop. And with that, we need 2 scope probes where you measure basically the input and output on that resistor. Now, once you have those connections, you end up with a plot that looks a little bit like this one, where we have on the top is the Bode plot, and on the bottom was the last measurement I think the scope took. And you can actually see the input signal looks nice and clean, and the output signal is getting kind of noisy because it's probably getting rejected. The green plot is the gain, the red plot is the phase. And in this case, you could put markers and find that 0 dB point on the gain plot, or the negative 180 on the phase plot. But if I just cheat and use the oscilloscope, I can see that I have a gain margin of 53 dB and a phase margin of 41. 40 degrees. Okay, so we have a little bit of homework to go do after the webinar to find out why is our phase margin so low, but at least we know we have somewhere we have to go and look. Okay, so measuring the control loop, gain margin, phase margin, you want at least 10 dB of gain margin and 45 to 90 degrees of phase margin in general. Okay, moving on. Let's talk a little bit about measuring impedance. And one of the comments, so impedance is another measurement that's going to make use of a Bode plot. The key difference between the last stuff we were talking about is that it's measuring impedance, so the resistance. We're going to be measuring, ideally, milliohms of resistance inside of our power distribution network. It turns out PDN is an interesting measurement because it helps us see things like high Q resonances, a poor control loop stability, and it gives us ideas on the potential paths for noise to get into the PDN. And so it's a really powerful measurement that normally would have only been done with VNAs. And so what I wanted to talk about is on Tektronix oscilloscopes, we actually have the ability now to do this impedance measurement. Compared to a VNA, there's 2 significant advantages. The number one is the frequency range. Oscilloscopes are naturally DC and are capable of DC measurements. So you can go from DC to a gigahertz. And like I said, you can go from 100 megahertz, which is probably the built-in frequency, to 500 megahertz or 1 gigahertz using external hardware. But the key there is that you can go all the way down to DC. Also, oscilloscopes are extremely versatile. All of the measurements we talk about today can be done with an oscilloscope, and there's actually one measurement we're going to talk about that you cannot do with the VNA. The one thing I didn't want to rate is ease of use. I'm a time domain person. I consider myself an oscilloscope nerd. So naturally, I think oscilloscopes are easier to use than VNAs. But if you have a frequency domain or RF background, you might have a different opinion. I think if you're starting from 0, the oscilloscope and the measurements you do within the oscilloscope are going to be easier than a VNA, but I can understand that not everybody has that as their opinion as well. So I decided to call that one a draw, even though I would prefer to say the scope is easier to use. Okay, so how do we make this 2-point measurement with a scope? Well, there's a couple of things that we need. Obviously, like almost every other measurement, you have to have a device under test, and you need an oscilloscope with a waveform generator. But the 2 special pieces of equipment that we'll need are, first, what we call an active splitter. So we recommend one from a company called Picotest. This device takes the input signal, and then it outputs the signal at the same amplitude as the input, but phase matched across 2 channels. And so this is a little bit different than a, say, power divider, which might reduce the out amplitudes by 6 dB, but they may also not be perfectly phase matched. And so since we're doing this with an oscilloscope, it's really important that we get 2 copies of this signal and that their phases match as close as possible. So that's why we recommend this active splitter. One of those signals are going to go into the oscilloscope, and the other one will have to get injected into the DUT, with the other side going into the other channel of the oscilloscope. However, it will need to go through something to isolate I cannot advance the slide. Okay, I'm not able to show the highlight. So okay. All right. Where I was going with this is, so I said we go through this power splitter, which creates 2 copies of the output. One goes through the DUT, one goes to the scope. The one that goes through the DUT, before we connect that to the scope, we do need to isolate its ground so that we don't create a ground loop. Remember earlier when I said we're measuring impedance, we're going to be measuring in like the milliohm range. And any kind of current that is going through the shields of the cabling that we're using is going to upset the impedance measurement that we're making. And so this common mode transformer, again, another device from Picotest, it will essentially isolate the ground shielding so that we don't end up with any ground loops while making this measurement. You can make the impedance measurement without it, but you're going to end up having a higher noise floor because of it. And then the last thing I wanted to point out is impedance is an interesting measurement because wherever you measure within a PDN or a circuit, you're going to get a different impedance value. And so this is one of those measurements where I really like using this 2-port probe, which is a probe that allows us to inject the signal on one side of a component and then measure the signal on the other. So we can get an actual 2-port measurement. And so I just wanted to point out that there are these 2-port probes available that make this impedance measurement significantly easier. Okay. So we hook this up, we get this measurement. What do we understand from this? So just like some of the others that we've looked at, there is bottom is frequency. Like I said earlier, the y-axis is impedance. To give you an idea, this flat portion is on the order of a couple of milliohms. Now, when we're looking at one of these impedance graphs, we know that anytime the impedance goes down and frequency goes up, that's typically a capacitive element. And on the other side, when the impedance gets higher and the frequency goes up, that's typically a inductive element. And so in this case, I think we're seeing the bulk decoupling capacitors as well as the inductive elements of the PCB. The middle section where the response is flat, this is where the output impedance of this PDN is going to have the lowest amount of noise in terms of frequency range, because it's basically the lowest impedance for these frequencies to find their path to ground. Now, if you're new to looking at this kind of measurement, what you might not realize is this is what's called an off measurement, meaning our power converter is currently turned off. And I can tell that because we can see the decoupling capacitor effect over on the left. If you make this same measurement while the power converter is on, and just a warning because the scales are going to be different, this is a different circuit that I'm looking at here. If you look at a impedance plot while the power converter is actually on, you'll notice we don't have that capacitive drop on the low frequency side. In fact, we're basically flat up until, let's call it 100 kilohertz. And what's going on here is the power converter is actively driving a low frequency or low impedance up to about 1 kilohertz. And then the next dip is where the multi-layer ceramic capacitors come into play. That's their ESR, and that's where they're actually bringing the rest of the PDN's impedance down. And so I just wanted to point this out because there's a difference in the two measurements, on versus off. And in most cases, you do want to make a on and off measurement because remember, components like multi-layer ceramic capacitors or MLCCs have a DC bias effect where the applied DC from the output of your converter will cause their capacitance to change. And you might actually see these impedances shift around. All right. When I think of impedances and I think about things getting injected into a circuit, my mind always goes to power supply rejection ratio. And the reality is this is a relatively simple measurement to make in principle. One of the reasons it's really powerful in a PDN is because it's another way for us to look at control loop stability, elements of the VRM itself, PCB elements, and how does the load affect the regulator. If you just go and measure the PSRR of a regulator by itself, that's one important and useful value. But seeing it in a system response can tell you a lot about what's going on with the rest of the system. Like I said a minute ago, it's a relatively simple measurement. You need to insert a signal into the input of a device under test and then measure the output. And the idea is you can use something like a line injector to inject a signal onto the input. And then we measure the output to see, does that signal make it through? If not, it got rejected. Now, since this is a lot like some of the other measurements we've already talked about, I'm just going to skip right to what does a graph of it look like. And it looks like a Bode plot like we've seen before. What we're showing here is across frequency, how much of that frequency content got rejected from the PDN. And you could use markers again, but if we just go and look at this, we're going to see something that we would expect. At low frequency, it has a very high rejection, 104 dB. And at relatively high frequency, probably as we get closer to its switching frequency, its PSRR drops to, its rejection drops to 55 decibels or dB. Okay. All right. So the PSRR is important because nothing we design exists in a vacuum. And so when I start to think about, well, why would I even want to measure the PSRR? It's because I want to think about what is the source that I have coming into my converter, and then what is my load going to be? And this busy graph helps us visualize the point that power distribution network design and characterization, unless you work for a converter company, doesn't just stop at the output. Eventually, it's going to get connected to some kind of load. And in many systems today, it's a digital load that has a lot of high-speed signals in it. And typically, when you think about high-speed signals, that's where people really worry about what's the jitter on those signals, because that typically will show an overall performance. And so one of the things we know is that any noise that either comes from or gets coupled into the PDN will typically show up on the edges of a digital output, right? In an ideal world, we would have a transmitter through a transmission path into a receiver, and the transmitter would put out this nice clean signal, and you'd get a nice clean signal on the output or at the receiver. I think we all know the reality is that doesn't happen. A whole bunch of happens to the signal, and you end up with something that's really noisy. Now, one of the questions that you might ask, or you probably have asked at some point, is what if I could remove the power supply noise? What would that received signal actually look like? So consider this scenario. Let's say you have a power distribution network that has two regulators, and regulator one has a really aggressive load, right? It has a lot of high current steps. It's high frequency. It's turning on and off a whole lot. So it's pulling really hard on regulator one, which is essentially pulling really hard on the power distribution network. And anytime you have a change in current, you will typically see a change in voltage, which the regulator two has to handle. Starting to sound familiar, PSRR, the impedance of the, so a couple of things should sound familiar, I meant to say. The impedance of the PDN network, what's the PSRR of the regulators, stuff like that. So regulator 2 is getting affected by this aggressor device, and then it's going to pass a little bit of noise into the victim, right? And so one of the questions we might ask is, what if we could remove the noise that aggressor causes? How much benefit would we get on our victim signal? And this is where I think this is just one of the coolest measurements you can make in terms of a PDN when you think about it from a system level design. So we have software on our oscilloscope that can take a measurement on a power rail and on a high-speed signal. And if it's a serial signal, we can do clock recovery to generate an eye diagram. And we can look at a super busy screen like this one. Now, in this case, let's break this down. The top of this screen is the signal we measured. So the eye diagram is the signal as measured. We recover the clock, generated an eye diagram. The histogram is of the jitter in that signal, and then the spectrum are the jitter components. Now, if you haven't seen a jitter spectrum before, it's like an FFT, but it's not of the original signal. It's of the jitter components. And so, for example, there's a big spur at 100 kilohertz, which tells me there's 100 kilohertz switching noise that is causing jitter on our eye diagram. So this is how we measured the signal. Now, if these spurs are from a power supply rail, maybe the rail that we're measuring, we can go ahead and remove all of that noise. And that's what the bottom of this screen was showing, is we have emulated what would that digital signal look like without the power supply noise getting injected into it. And so we see a nice clean eye, we see a bimodal jitter distribution, and far fewer spurs in the jitter spectrum. And so where this is incredibly powerful and useful is if you see a jitter issue, you can actually do a kind of a what if scenario that says, if we go and invest time and effort into fixing this part of the circuit or this part of the power distribution network, what could the potential result be? By the way, you can also apply notch filters to this result so that if you could only fix maybe one aggressor, what would the result be? Would it be worth going through and making that measurement? The last thing I want to say on this one is there's a lot more to this topic on PSIJ, and so we have some materials on how to make that measurement. I just wanted to introduce it to you because it does tie together. If I have these noise components in the PDN, how could they affect the final circuit? And then how could I look at what fixing those problems would look like in my final system? All right. I showed a lot of products in the presentation. If there's any of the pieces you're interested in, these are the part numbers that will probably get you to the information you need. If not, feel free to reach out to me and I'll be happy to answer or address any of the measurement setups that I showed. I didn't want to get into the details what all the part numbers were while we were talking. So in summary, power delivery networks are the components between a source and a load. By using frequency response analysis and Bode plots, we can measure a converter's stability. We can look at its output impedance. We can measure its power supply rejection ratio. And those are really interesting measurements to combine with power supply induced jitter, because then we can gauge how much of the potential improvements we can make to our system will apply at a system level. All right, in just a moment, I'm going to take a look at the questions that have come in. I think, Leon, you want to cover a couple more things before we get to the Q&A.
Yes, thank you, James. Just another reminder here. You will find a couple of items on the resource tab, including a PDF of the slides from today, as well as an application note from Tektronix. Electro Rent, in addition to Endeavor, will be sending a follow-up email out next week with a link to the published recording and all 3 webinars in this series. You can also engage with both Electro Rent and Tektronix on LinkedIn. We encourage you to follow our company pages to stay in touch. Visit electrorent.com to learn more and contact us. Now, let's turn our attention to some audience questions. And
very good.
Billy, I think you've got some questions for us.
Yes, definitely. A few of you have already submitted questions, so we're going to jump right in. As a reminder, if you'd like to submit a question, type your question into the question window on the side of your screen and hit the submit button. So to start with, how do you control the magnitude of the injection signal at lower and higher frequency here?
That's a good question. I kind of glossed over that. So in our software, and I think and I've seen this in a couple other solutions, not all Bode plot software for oscilloscopes allow this, but like in ours, you can open up a table and say at this frequency or in this frequency range, use this amplitude. And so you can change the amplitude as you get to either lower or higher frequency. It's an option. It's an option in the software. I just didn't get into that detail.
Okay. Of the measurements shown, what's the most important one?
Well, I think The easy answer is all of them. Yeah, so I like that question because I actually hear Steve Sandler. He's the managing director of Picotest. He's also an expert in signal and power integrity. And I've overheard him say before, measuring impedance of a PDN is the most important measurements. If you know what you're looking at, you can actually see things, like I said earlier, is you can actually see control loop stability problems. You can see potentials for where noise is going to enter into the system. You can actually see a lot of the things just by looking at the impedance of the system. Again, I think the caveat there is you do have to really know what you're looking at, but the information's there. And so if you can only make one measurement, impedance is probably the one that I would consider. So yeah.
Okay. What if you don't have a resistor in that control loop measurement?
Oh yeah. Let me pull that slide back up. I know where this question is coming from because I've had this question before. So when I was talking about measuring the gain and phase margin, I did mention that you do need to have a resistor in the control loop, within the control loop, that we can inject a signal onto. Sometimes it works out that there's a shunt resistor that you can put in, especially to put in for this measurement. But sometimes you may not have that available. So one of the options would be to use an active injection transformer. That's a different type of transformer that Picotest sells. In that one, you don't use the resistor, but you still have to make a break between the output rail and the top of the feedback network. So that'd be one way. And then there's another way, and if anyone's interested in this, I would love to hear from you. There's a technique called NISM, non-invasive stability measurement, and it is an algorithm that can measure the output of the converter and come up with what its stability parameters will be without breaking the control loop. And so it's something that we've been looking at and trying to decide if we're going to put it into our scopes as a measurement or not. And so if that's something that you're comfortable making or you're interested in seeing, I would love to hear from you.
Well, very good. Unfortunately, we've run out of time. For those questions we didn't have time to answer, we'll be getting back to you via email. Please remember to take today's exit survey if you have not already done so. Your answers help us craft future events and to continue to bring you engaging content. This concludes today's presentation. On behalf of Electronic Design, I'd like to thank James for his presentation today, Electro Rent in partnership with Tektronix for sponsoring today's webinar, and of course, all of you for joining us. Have a great rest of the day.